Whether you're on a computer, your phone, or even driving a modern car, you're interacting with a legacy that's about 50 years old. And I'm talking about the C programming language. At the heart of this whole story is this little book, which, well, it became an absolute legend. So let's dive in and figure out why a language from the 70s is still one of the most critical pieces of tech we have today.
Even the authors themselves knew what was happening. This quote right here says it all. When this book first dropped, computers were, they were enormous. They took up entire rooms. And today, the phone in your pocket has way more power than one of those old mainframes. It's just wild. And that's the world C was born into. And, really, the world it helped build.
So, this revolution, what was it all about? Well, it was a massive change in computing, and it created a brand new problem. A problem that the older programming languages just weren't equipped to handle.
Okay, so the old way was big computers, right? These giant centralized mainframes that a whole organization would share. But the world was shifting towards personal computers. Suddenly, computing power wasn't just in one room, it was on people's desks. It was becoming, personal. And that meant we needed a new kind of language. Something powerful, sure, but also something portable. A language that could run on all these different new machines, not just one specific piece of hardware.
And right on cue, that's where C comes in. See, this wasn't some project cooked up in a university lab for theoretical reasons. Nope, C was a tool built for a very specific, very important job. A guy named Dennis Ritchie over at Bell Labs needed to build an operating system. You might have heard of it. It's called Unix. C was his answer. It was the practical, lean, and super powerful language he created to build the very software that would drive this whole new era of computing.
So to really get why C took over the world, you got to understand its philosophy, its core ideas. The thing is, it wasn't trying to be the biggest, most complicated language out there. Actually, it was pretty much the exact opposite. These principles here, they're pulled right from the original preface of the book. The language was all about economy of expression, so writing less code to do more. It had modern float control and data structures and a rich set of operators. But that last one, absence of restrictions, that is the big one. That's the one that changes everything. It basically means C trusts you, the programmer, completely, for better and sometimes for worse.
And here it is, the most iconic little piece of code in programming history, probably, the legendary Hello World program. This is just a perfect example of that economy of expression we were just talking about. Look how short it is. With just one main command, you're telling the computer to do something. It's so direct, so simple. And for millions of programmers, this was the very first program they ever wrote.
And this quote, this really gets to the core of it all. C isn't a very high-level language. It's not big. Its real power, its secret sauce, comes from what it doesn't do. It doesn't put a bunch of safety nets around you. It doesn't hide how the computer actually works. It just gives you the raw, powerful tools and says, here you go, you're in charge. And that absence of restrictions is exactly why it's so incredibly fast and flexible, even today.
Okay, so let's talk about how C actually gives you all this power. What's the secret ingredient? It's all about giving you direct access to the computer's memory. And the way it does that is through a concept that is famous and maybe a little infamous, something called pointers.
Seriously, if you want to understand C, you have to understand pointers. It's that simple. So think of it like this. Your computer's memory is like a huge street with a bunch of houses, all with addresses. A regular variable is like putting something inside one of those houses. But a pointer doesn't hold the thing itself. It just holds the address of the house. And because you have the address, you can go directly to that exact spot in memory and mess with whatever's inside. It's incredibly direct.
So here's a really simple way to see that difference in action. On the left, you've got an array. Think of this as the actual container, the box itself, that holds all the letters of our message. But on the right, you have a pointer. The pointer isn't the box. It's just a little piece of paper that has the address of the box written on it. So the array is the data, while the pointer just, points to the data. Getting this difference is absolutely key to C programming.
And this is where things get really wild and honestly a little mind-bending. This one single line of code, look how small it is.
It copies an entire string of text from one place in memory to another using pointers. It's maybe the most perfect example of C's economy of expression. It's dense, it's powerful, and depending on your point of view, it's either beautiful or absolutely terrifying.
So, how on earth does that little line of code actually work? It looks like magic, but let's break it down. It's actually doing three things at once. First, it takes a character from the source pointer and copies it to the destination pointer. Simple enough. Second, it checks the value of the character it just copied. If that character happens to be the special one that marks the end of a string, the whole loop just stops. And third, and this is the really clever part, it automatically moves both pointers one step forward so they're ready for the next character. Copy, check, and move forward, all in one go. It's genius. But, and you knew there had to be a but, right? All of this power, all of this freedom, it comes with a pretty big catch. C gives you a toolbox full of incredibly sharp instruments, but it doesn't give you any safety gloves.
So what happens when you have this much freedom? That's really the core conflict of C, isn't it? On one hand, you can write super efficient, amazing code. But on the other, you can create bugs that are so subtle, so hard to find, that they become complete disasters. The language just trusts that you know what you're doing.
And this quote, which comes straight from the C manual, is a fantastic example of that. It says the order of evaluation of expressions is undefined. So what does that even mean? It means if you write a line of code that does a few things, you can't be sure in what order it'll do them. It might work one way on your machine, but break completely on your friend's machine. C doesn't care. It prioritizes raw speed and lets the compiler figure out the fastest way, which puts all the responsibility right back on your shoulders.
Here's another great example of C's whole philosophy in action. Let's say you have a function. By default, when you give it a piece of data, C doesn't give it the original, it sends a photocopy. This is called passing by value. That means the function can mess with the copy all at once, but the original is safe. If you actually want the function to change your original data, you have to be very explicit. You have to give it a pointer, the actual address, so it knows exactly where in memory to make the change. Once again, no safety nets, no assumptions. You have to say exactly what you mean.
So as C just exploded in popularity, this whole trust the programmer idea started to cause some problems. It was a bit like the Wild West. Different people were writing different compilers, and they all interpreted the unwritten rules of C a little differently. This led to chaos. Code that worked on one system would fail on another. It became clear that C needed a single official rulebook.
For years, that little white book was basically the Bible. It was the de facto standard, meaning everyone just kind of agreed to follow it. But as you can see on this timeline, that wasn't enough. By 1983, the American National Standards Institute, or ANSI, put together a committee. Their whole job was to hammer out a formal, official standard for the C language, one that wasn't ambiguous and worked the same on every machine. And in 1989, they finally did it, giving us what we now know as ANSI C.
And this new standard wasn't just a rubber stamp. It made some really important changes to make C stronger and safer. For example, before, you might declare a function just by its name. But ANSI C introduced function prototypes, which forced you to spell out exactly what kind of data the function expected to receive. This was a game changer, because now the compiler could actually check your work and warn you if you were using a function wrong. It also officially added things like the void star pointer, which is a kind of universal generic pointer, making the language way more consistent.
When you get right down to it, the ANSI standard is what cemented C's place in history. It was a total game changer. By making sure C code was portable and reliable, it turned it into the bedrock of modern computing. And that stability is the reason why, even today, C is at the core of pretty much every major operating system. It's in the tiny embedded systems running your car or your microwave, and it's even the foundation that so many newer, more modern languages are built on top of.
And that brings us right back to today. The entire story of C is a story about a trade-off, isn't it? It gave programmers absolute control and blistering speed, but the price was safety. A lot of modern languages have swung the pendulum way over to the other side. They prioritize safety and convenience above all else. So that leaves us with a pretty big question to think about. In making everything safer, what have we gained? And what have we lost? Have we lost some of that raw power, that deep understanding of the machine?
It's a question that really gets to the heart of how programming has changed over the last 50 years.